Hey guys, today we're doing an A2 mechanics paper. The first question, we are throwing a stone from the top of a high tower. So it's going to be classic motion under the influence of a gravitational field. There it goes. So they're looking for when this thing is at a point where it makes this angle of 30 degrees below the horizontal. Well, that means that if you draw a horizontal line, this thing subtends 30 degrees like so. So it's on its way, it's in the path, and right now that's tangent to it. So we can think about the relationship between Cartesian coordinates and polar coordinates, which may seem a little weird to you. But the important thing is that when you have something that is moving with some speed, say at the beginning of some projectile motion, this is not this case, but in some other case, you would have an x component and a y component, and the angle of you'd have some resultant speed and some angle theta, and you would find the resultant speed, also called the radial component. It's essentially conversion to polar. It's like finding the resultant and the angle. That's going to be equal to the square root of vx squared plus vy squared. And the angle is given by inverse tangent of vy over vx. Now you can convince yourself that this is true, that if you take vy over vx, that's equal to the tan of theta, and that r is just Pythagoras. So the same thing is true over here. You will have some tangent velocity, like so, and you know that there is a x component and a y component, and that angle is 30 degrees. And now we need to know what vx and vy are. Well, vx is a constant because there are no forces acting in the x direction. That's the key to these little problems, is that we're only moving under the influence of gravity, and gravity only acts in the vertical y direction. So vx is a constant. And what is it? Well, it we can just call it some, we'll just call it vx because we'll find these things will cancel. And that means that we can write x of t as just vx times t, constant acceleration equations where the acceleration is 0. Now vy, well, that equals vy naught, which is 0, because at the beginning it hasn't been accelerated. You just sort of you fling it off only in the x direction, so it has no y component at the beginning, minus gt. So that y of t, it's sort of integrated, in fact exactly integrated, is minus a half g t squared. Okay, so you can see that this is just distance moved where there's no initial velocity, no initial displacement, and you're only moving under the force of gravity. Now we can solve for theta. So theta is going to be the inverse tangent of vy, which is minus 1/2 g t squared, all over vxt. Okay, so we have g, we have t, and we have theta. So we just need to invert this equation, and we get that vx is equal to minus gt over the tangent of minus 30 degrees. And you will find that the minuses cancel. The tan of minus 30 is going to be negative as well, so you get the correct answer. So the key to this was being able to convert between Cartesian and polar coordinates. The idea of going from some distance to x and some distance to the y to saying rotate a certain amount and head out. But it's exactly the same idea as you would converting between spherical coordinates and Cartesian coordinates in 3 dimensions. You should be familiar with that, but otherwise just memorize the formula. Okay, question 2. So a particle P is attached to one end of a light elastic string. So this is our scenario. Our string and our particle P there. And now we've got, what forces do we have acting on this? Well, we have the mg, the weight of the thing, and we have the tension in the string. And the tension in a string is, if you look at your formula booklet, is given by lambda x over L, where lambda is the modulus of elasticity, x is the amount that the string has been stretched from its natural length. So not just the length that it is, but the difference between that length and the natural length. And the natural length is L on the bottom. So they want us to find the distance from A to P. And to do this, we realize that the thing is in equilibrium, therefore T must be equal to mg. So that means that x is going to be equal to mgl over lambda, which is 0.125 meters. Now remember, that's just the amount that it's been stretched. So its natural length is 0.6. So 0.6 is somewhere here. And then it's been stretched a little extra amount. So the AP distance must be 6.125 meters. Okay, so now they raise P to A and release it from rest. Calculate the greatest speed of P in the subsequent motion. So what this is harmonic motion, elastic motion, because the string is elastic. And the greatest speed that something achieves when it's going through this harmonic motion, like springs vibrating backwards and forwards, or things going in and out of bowls and so on, the greatest speed is at the equilibrium point. So the point where if you placed it there, it wouldn't move. If you place it there at rest, it wouldn't move. But of course, when it's actually passing through it, it is moving because it's got all this momentum. So if I have my start point and my equilibrium point, as I'm coming down here, so I've got this, I'm attached to an elastic string. As I'm going down here, the string is slack, but gravity is accelerating me downwards. Here I meet equilibrium. From this point onwards, gravity still pulls me downwards, but it's being fought by the elastic string. So I'm actually going to be slowing down. My acceleration is going to be less and less, and eventually it's going to force me to come back up again. So we're looking for where the P is, where the thing is hanging at equilibrium, where it was hanging at rest before. So a distance AP. So this is a conservation of energy question. So what energy is it right when it's at the top? Well, remember that this distance is AP. And when it's right at the top, the string is slack, so there's no string elastic potential energy. It's at rest, so there's no kinetic energy. The only energy is gravitational potential energy. So at the beginning, the energy is just mgh, which is where the height is AP. Now that must be equal to its energy at a later point, because this is a conservative system. There's no friction. There's no channeling of the energy to any other place. Everything all in the ball. So so you've got this, mg AP must be equal to, well, what's happening when it's here? It's moving, first of all. It's now got no gravitational potential energy, bearing in mind that it'll have gravitational potential energy relative to the ground, but with gravitational potential energy, we only care about differences. So we just measure the difference between here and here. So we set this to 0. You can move the 0, and it's hard to think about sometimes, but it's very arbitrary where the 0 is for for potential energy. So we just pick a 0, and then we talk about differences. So the difference in gravitational potential energy between those two places is mg times AP. And that must be equal to the kinetic energy plus the potential energy, elastic potential energy inside the string, which if you look on your formula booklet is Lx squared, lambda x squared over 2L. So if we know m, we know g, we know AP, we know m, we know lambda, we know x, we know L, so we can solve all of this to get our V, which is about 3.6 meters per second. Okay, so in that question, conservation of energy and using the formula booklet thing for the elastic potential energy inside an elastic string. Okay, question 3. So the first question is asking for us to resolve forces. It's worth 4 points, but I think, it's actually pretty straightforward. So they're just, for the first question, you're just treating the rod as like a single system with some forces acting on it. And so you can resolve horizontally and vertically. So let's say this force F, we know that this component is going to be F cosine of 45, and this component F sine of 45. And the same thing over here. This is going to be 10 cosine 60, and that one is going to be 10 sine of 60. And this thing is in equilibrium. It's at rest, so we can equate the components independently. So we know that F cosine of 45 degrees must be equal to 10 cosine of 60 degrees. So we can solve this, and that'll give us the value of F. And the other thing we need to know is that there is a weight of the rod acting downwards. So we can picture all these forces just sort of balancing out. So in the vertical direction, we've got F sine of 45 degrees plus 10 sine of 60 degrees minus the weight is equal to 0. And we know what F is now, so we can solve for the weight. And that's what you have to do. So now comes the tricky part. Well, what I think is trickier. You may well disagree. So this is about thinking about the moments about A. So I'm going to redraw, or maybe I can maybe do it on this drawing. So at some point we're going to have a center of mass, and they've said that the rod is non-uniform. So that means the center of mass is not at the center. It's a center of mass, but it's not at the center of the rod. It's, like imagine a rod. If I had, some rod which was super dense towards this end and then super light, the center of mass would be over here. It wouldn't be in the middle. It's like a seesaw with like someone sitting at one end and no one sitting at the other end. The center of mass is going to shift. So the center of mass is somewhere over here, perhaps, let's say, and the weight is acting downwards. Now, if we're looking for moments about A, you remember how to get moments. Well, moments, you take a moment about a point, and you measure the distance from that point to the line of action of a force. So we're firstly going to resolve this weight like so and like so. And this is the line of action of the, so moments only care about things that are at right angles to this, lever. That if they're going along the lever, that makes no difference to whether, the moment's all about yanking something, cranking something around a pivot point. So it doesn't care about the stuff that's along the rod, because that will just stretch or shrink the rod. Irrelevant. What we care about is this guy here, this one that's at right angles to the rod, and that has this line line of force. So I'm going to call the distance between A and this guy, I'm going to call this x, and that's actually what we're looking for. We also know that there is this force F. Now, don't be deceived. F is not acting at right angles because the angles don't match up. The F, the component that we want, is sort of like this. And you'll find that that's given by F cosine of 15 degrees, because that is the difference over here between 45 and 60. So this whole thing, so what we're actually taking is this component and then rotating it. You can do it a bunch of different ways, but what we want is this little cosine of 15 to make the difference. So you're just resolving it along this direction, and 15 degrees there. So remember that this one is the hypotenuse. This is the F. And then we're resolving it along. I know I didn't. Okay, let me erase that. I'll make it a bit more straightforward. A little more clear. So that is going to be, I'll use another color. It's going to be a right angled triangle. And we're projecting out. We know that this is 15 degrees because if we, let's draw a line down there. So we see that that's going to be 60. Therefore that whole thing has to be 60 because that's going to be 30. And therefore this whole thing has to be 60. So that difference there between the 45 and the 60 has to be 15. Anyway, the point is that this thing here, which is one side of this narrow triangle where the hypotenuse is F, is F cosine 15. Right. The other point to make is that this 10 Newton force does not provide any moment about A because it is acting through A. So, you know, if you've got some rod hanging on a pivot, nothing you do at the pivot itself will give any swing to the rod. You have to always, like, you know, have your hand at least a little further down. So we're looking for moments. Moments. About A. And we know that they must all add up to 0 because otherwise the thing would be swinging. So we've got the weight times x. So that's this one here. And in fact, we don't want the weight, which is the one acting down. We want the component over here. And that is W times, and then we'll find out what angle that is. If that's 30, that's 60, that's 30 again. So it's W cosine of 30. This is just fiddling around with angles and drawing alternate angles and all sorts. And that's times x. So remember, you multiply, the moment you multiply it, the force that you're looking at times the distance between the axis, the axle point, and the line of action of the force. So let's write this more clearly. It's W cosine 30 times x must be equal, sort of balancing out, F cosine of 15 times 0.5. And we know W, we know F, so we can solve for x, and we get it like so. Okay, question 4. Now this is again about sort of the motion of a projected particle, except this time it's being projected sort of upwards, and it's sort of going over, hitting the ground, losing some energy and bouncing, and then hitting the ground and staying at rest. So this requires a little more thought than the last time. But firstly, in this question, they want the time at which this thing meets the point A. So it goes from O to A. And when it sets off initially, it's got the speed, resultant speed 20 meters per second, and it's off at an angle of 30 degrees. Okay. So, what do we know about when it's at A? What do we know about its velocity? Well, we know that whenever you've moved in a parabola and there's no air resistance or anything funny, your velocity v, vy, velocity in the vertical direction, is exactly opposite when you reach the other side, because you just got up and then been accelerated. Up here, your vertical velocity is 0, and then you get accelerated all the way down to exactly the same spatial height. So everything is symmetric. You must have the same but opposite. So we know that Vy at some, TA is equal to minus Vy at time 0. And this must be equal to Vy at time, so from the constant acceleration equations, must be equal to initial velocity minus gt. So we're saying that the negative of the initial velocity is equal to the initial velocity minus gt. So if you rearrange this, you'll see that means that that t is therefore equal to 2 copies of Vy at time 0 over g. And that's going to be, so Vy at time 0 must be equal to the resultant, the magnitude of velocity, times the sine of 30 degrees. So this is 40 sine 30 over g, which is 2 seconds. Now, on the other hand, in the x direction, there are no forces acting. So like before, Vx is just a constant. It's not actually a function of t. And so it is always equal to 20 cosine 30. Bear in mind, this is just, I'm just talking about these two things are only relevant between O and A. We'll see in a second that something slightly different is relevant between A and, I guess, B. So the distance traveled in the x direction is just going to be Vx times t, because it's just velocity times time, constant velocity. That's how you get it. So this is going to be 20 cosine 30 times 2, which is 40 cosine of 30, which is 34.6 meters. Okay, not too bad. So now they're sending it on this second part of its journey, and they're asking us to talk about its motion and its lost energy. So it's come down here, and it's not going to get so high the next time. What they're telling us is that the velocity in the vertical direction, they haven't said anything about the horizontal direction, but in the vertical direction, it's now 8 meters per second. So what are they asking us? They're asking us for the first and last times after projection at which the speed of p, so that means the resultant velocity, like the sort of Pythagoras hypotenuse between Vx and Vy, is 18 meters per second. Well, we know that at the beginning it was 20, so therefore it must sort of decrease to 18 somewhere here. And then at some point later it's going to be minus 18, because it's going to it's going to be at over here. So let's look at it mathematically. Again, all this time we're taking Vx to be constant. So yeah, which is 20 cosine of 30 degrees, which we're just going to write as 10 square root 3. And Vy, it's going to depend on where we are. So if we are between O and A, i.e. between t is greater than 0 or less than or equal to 2 seconds, This is given by 20 sine of 30 minus gt. Makes sense, right? That's just the, it starts off with 20 sine of 30, which is actually equal to 10. And then minus gt will take you there. Now, exactly the same thing applies between A and B, which is t greater than 2 seconds, but less than, well, we'll find out in a second. And this is given by initial velocity of 8 minus g, and then the time that has elapsed since it left A. This is a subtlety, not the time since it left O, but this gravity has been working to eat away at the velocity since it left A. You know, here this took care of everything between 0 and 2 seconds. Now from 2 seconds, we're starting with a fresh 8 meters per second, and time is sort of elapsing from then. So in terms of the time that has elapsed from O, this is t minus 2. So at A, I'm actually at t equals 2 seconds, but I'm 0 seconds into my new regime. So I have to subtract 2. If I'm halfway through, or at the end, if I'm, say, 1 second from A, then I'm actually 3 seconds in terms of t. So have a think about this and just make sure that you understand it. And the point being that Vy, we can work out. I mean, who cares? Some TB, some final time. So, in fact, when it's equal to minus 8, so let's do it as a check, because that'll help us make sure that we've got the right answer later on. So when t is equal to tf, t final, tb, then Vy is equal to minus 8. Remember that same principle, that it starts out with a vertical plus 8, that at the end it must be minus 8. And so we have minus 8 is equal to minus g of t minus 2. So t is equal to swap. Let's do minus 8 plus 2g over g, which is 2.8. Okay, I think that's actually wrong, but I can't figure out why. So let's ignore that for now, and I'll think about it. If we've got time, I'll come back and do it properly later. I think I just missed something. Wait, yes, no, I see. Oh, I'm such an idiot. It's because you have, it was minus 8 is equal to 8 plus blah, blah, blah. So this is actually 16. And so this becomes 1.6 plus 2, which is 3.6 seconds. Okay, great. Happy. So this is 3.6 seconds. That's the final time. That was just as a nice and easy check, and then I got it wrong. So we have two possibilities for two equations for Vy. So what is our speed? Well, speed is given by the equation square root Vx squared plus Vy squared. And we're asked for when this is equal to 18. So you can see this is a magnitude. It doesn't care what direction you're at. So we'll have it when we're here, it's going to be plus 18. Here it's going to be minus 18. Here it's going to be plus 18, and here it's going to be minus 18. But what they want from us is the first and the last times. So it's that one and that one. Anyway, so if Vx is constant and always equal to 10 square root 3, then we can rearrange this and realize that this means this is a condition that Vy must be equal to plus or minus 2 square root 6 meters per second. So we know what Vx is, it's always the same. So requiring this is equal to 18 gives us this condition for Vy. So if we plug this in, we know that the very first time it's going to be plus 18. And that's going to be during the first 2 seconds. So we plug in, and Vy is positive, as you see. So we're going to plug in Vy equals plus 2 square root 6 into the first equation here, 10 minus gt. And that's going to give us t is equal to 0.51 seconds. And we know that the very last time Vy is negative because it's heading downwards, and it's going to be in this regime, the second regime. So there t, if we put that in, we get that t is equal to 3.29 seconds. And this is where the check comes in, because we see that this is less than the end time, 3.6, which is great. Otherwise we'd be in trouble. So you see that there will be 4 solutions. There's a plus and a minus, and there's one each of those for each regime. So each regime has there's 2 regimes, and each one has a plus and a minus solution, and that refers to those 4 possible points. But we only care about the first and the last ones. Okay. So now we have another one of these ramp problems, but it's more of a differential equation problem. So we're given the idea of the equation for a force as a function of time, and we're told that we're told this thing is on a ramp, and it's released from rest. Well, what's going to be acting on it? Well, the mass of the object is going to be acting downwards, and along the plane, that is going to be mg sine of 30 degrees, and mg is just 4, and sine of 30 is a half, so this is equal to 2 newtons. And then we're also told that there is a force acting up, like so, and this is force F, which we're given here. So our total force, F net, is going to be equal to the force F, 3e to the minus t, minus 2 newtons, which was the component of the weight in that direction. Now, what is the force? Well, force is just mass times acceleration. And what is acceleration? Just the rate of change of velocity. So you can see that we then just divide by m, which is 0.4, and we get we recover the equation that they want us to. Now they want us to integrate. So we do separation of variables. So that means you take all the v's on one side and all the t's on the other. Now there's no v dependence on the right hand side of this equation. There's just t's. So we'll go dv is equal to 7.5 e to the minus t minus 5. And we're going to integrate these. Oh, that's dt. I've taken the dt from there to there. And as I said before, there's 2 ways of dealing with boundary conditions. So our boundary condition is that at time 0, the velocity is 0 because it's been released from rest. So that's rest gives a boundary condition or initial condition, and that allows us to fix the constant that comes out when you do an indefinite integral. And in this case, it means that t is equal to 0 is associated with the velocity being equal to 0. So you can either solve in these indefinite integrals and add a constant, and then insert the values and then solve what the constant needs to be, or you can just integrate them into the integral limits. So I'm going from 0, where the time is 0 and the velocity is, and they're both 0, to some later time where the velocity is v of that time. So I'm just going to integrate this. Well, on the left-hand side, that becomes v of t minus 0. So that's just v of t. And that's going to be equal to minus, so integrating the exponential function, minus 7.5 e to the minus t, minus 5t. I'm evaluating with this between 0 and t. And you can see that this is going to be equal to 7.5 minus 7.5 e to the minus t minus 5t. And where does this come from? Well, this comes from the lower limit where you've gone minus 7.5 e to the minus 0. E to the minus 0 is just 1. Pluses take over the minuses, and you get 7.5. So just be careful when you've got exponentials and you're evaluating between two limits and having integrated, because sometimes you're so used to polynomials that if your lower limit is 0, you just chuck all of the lower limit stuff away. Can't do that with exponentials, because e to the x evaluated at x equal to 0 is 1, not 0. Okay, this seems to be the same question. So, well, yeah, that's the same question. Sorry, that's a mistake. This should be question 3. And they want us to find the distance. So the distance traveled is as a function of time. Well, that's going to be equal to, yeah, okay, so I remember the question. The question was something like, what is the distance traveled when v is at its maximum? So v equals v max when dv dt is equal to 0. So that was just the original thing we were given, right? The acceleration. And this is the standard thing about maxima and minima of a function is when the first derivative is 0. So dv dt, that's this business here, is equal to 0. So you'll have 7.5 e to the minus t is equal to 5. So e to the minus t is equal to 5 over 7.5, which I think is 2/3. Yes, 2/3. So then you take the natural log of both sides and you get minus t is equal to natural log of 2/3. Oops. So t is going to be equal to minus the natural log of 2/3, which is same thing as the natural log of 2/3 to the minus 1, which is I know this seems silly, but it's just to make it easier, which is equal to the natural log of 3/2, which is equal to the natural log of 1.5. Just makes it a bit easier to write than dealing with minus signs. It's just using the properties of logarithms that you can absorb prefactors as exponents inside the log. So we know that we're evaluating this thing, we're integrating. So the distance is the integral of the velocity over time. And we're going from when it's traveled 0 distance, which is at time 0, to when it's traveled s distance, which is when the time is natural log of 1.5. So this is not s of t, this is s, just s, this distance we're trying to find. Well, now we're just integrating all over again. And we're integrating this guy here. Well, that's pretty straightforward. So we've got 7.5 t minus, so plus again, 7.5 e to the minus t minus 5 over 2 t squared between 0 and the natural log of 1.5. So you just need to evaluate this a little carefully. And you should get the right answer without too much trouble. Okay, question 6. What do we have? Well, we have this complicated looking object, and we always know you're going to be talking about toppling when you have these kinds of questions, because we've got these 2 points. So firstly, they're asking us about when this thing is about to topple forward under the weight of the bulge of the P on the point of toppling. So that means that we're taking moments about A, because that's where the thing would be turning on. Now this is all about finding centers of mass, and I'm going to be very careful here. Well, where is the center of mass? Remember, the centers of mass, you can divide the thing up into bits and then just sort of add the centers of mass, the weighted centers of mass all together. So where's the center of mass of the rectangle? Well, it's halfway up and halfway across. Pretty easy. And I'm going to give that a vector. This is the way I like to do it, even though sometimes I give a little more information than you need. But I'm going to measure for this question only. So be aware, for the next question, I'm actually going to measure from a different point. But for this question only, I'm measuring from A. So I'm going to call X rectangle, so position of center of mass of the rectangle. The X direction is minus 0.2. And the Y direction is 0.9. For the circle, the semicircle, hemicircle, I'm going to have to consult the formula booklet. And it tells me that when I subtend a sector of a circle by an angle 2 alpha, then then it'll give me my, I can't remember exactly what the formula is, but what you here are 2 alpha is pi. And I think you get, so in this case, x of the circle, I don't have the formula book in front of me, but this is what you will get is 4r over 3 pi. And that's the distance from A to the center of mass of the circle, which is about here. So the center of mass is here, and that one's there. And the vertical distance, well, it's just going to be, obviously, this thing is symmetric up or down, so it's going to be 1.8 minus the radius. So it's 1 radius short of the top. So 1.8 minus 0.4. Oh, wait, no, we haven't actually done the 0.4. Sorry, it's actually 1.8 minus r, because we don't know what r is yet. So now they want to show us that r is equal to 0.6. So what we do is the same thing as usual. We know that this is a mass. You can think of this as the mass of the rectangle being weighed down like that, and the mass of the semicircle being weighed down like that. And so here are the lines of action of their forces. And so moments about A, we know that these two things must balance. So this one, the semicircle one, is trying to rotate the thing that way, and the rectangle weight is trying to rotate the prism the other way. So we know that this is all about the mass of the so let's say, okay, let's do it properly. So we know that mass of the rectangle times g, which is the weight, times the distance between the rectangle's line of action of the weight and A, which is 0.2, must be equal to mass of the circle times g times 4r over 3 pi. Great. So you can see, of course, that g's cancel. The masses are a little more, require a little more explanation. Remember that mass is just equal to a density times a volume. Or in this case, we can just say a density times an area, because we're only looking at one slice. So we can just pretend we're, some unit depth prism, and we can write this in terms of rho, and then rho will appear on both sides because they're made of the same material. So we're just left with the area. So it's area of the rectangle times 0.2 is equal to area of the semicircle times 4r over 3 pi. Now this you can work out yourself, no problem. You'll get that 0.144 is 1/2 pi r squared times 4r over 3 pi. And this will give you 2r cubed on 3, and that'll give you that r is equal to 0.6. So the important thing was to take moments about A and to realize where the centers of mass were using the formula booklet for the semicircle. That was actually, that's not non-trivial. Non-trivial. Now, this bit's actually worth taking a little care about. Now, why is that? It's because they're talking about this force being applied to the prism acting at 60 degrees to the upwards vertical along a tangent to the semicircle at a point between D and E. Now, that's not a clear sentence. That actually takes quite a lot of parsing, and I think it's quite unfair. Now, here's D and here's E. So it's acting somewhere between them, and it's tangent to the circle. Like so. And in fact, why don't I do that in a nice purple? And when they say it's at 60 degrees to the vertical, oops, they're talking about this this angle here. So let me just erase some of this. So if that angle is 60 degrees, let me draw a horizontal line here. Then I've and here's another radius. I know there was a radius already there, but whatever. This is still a radius that I've just drawn. That's still R. So I've built myself a triangle here. And if that's 60 degrees, then that's got to be 30. And therefore that, again, is 60 degrees. Convince yourself that that's true. And because this is R, that means that this distance must be R cosine of 60 degrees. And this distance must be R sine of 60 degrees. And if you work that out, you'll find that that is 0.52 and that one is 0.3. Okay, so we've got this new force. And we can resolve it into a vertical component and a horizontal component. And we know that that is the line of action of the horizontal component, and this is the line of action of the vertical component. Why am I doing this? Well, the question is asking us about when the thing is about to topple the other way. So what that means is we're now taking moments about B, because this force is enough to make it almost topple the other way. So we are looking, in fact, we don't care about that. We are looking for all the things that could be providing a moment about B. So this one, this force P, the vertical component, which is P cosine of 60 degrees, that is acting at a distance of, so now I'm setting 0 to be I'm measuring distances from B now. That's what I care about. So this distance here is going to be the distance to the edge of the rectangular prism plus this distance R cosine of 60, which is 0.3. So this distance here is going to be 0.4 plus 0.3, which is 0.7. So let me put XP. This is where the relevant points that the P is acting like the relevant distances. So that in the X direction, 0.7. And in the Y direction, well, what's this distance here? Well, it's sort of this height, which was where the height of the center of mass of the circle is 1.8 minus r, plus this distance, which was the 0.52. And so that's pretty, that doesn't, take too long to work out. I should just put this as 0.255 and 1.8 minus r, where r is 0.6 is 1.2, just for reference. Okay, we're almost ready to do this. So we know that the moments about B going that way are P sine of 60 degrees times the distance, 1.72, plus P cosine of 60 degrees times distance, which is 0.7. So let's look at that again. P cosine 60 degrees was 0.7 away from B, and P sine 60 degrees was the other one, 0.5, 1.72. And those are the only ones that are rotating this way around B. The other two, the red ones, the weights, are rotating the other way. So moments rotating that way are, so by the way, if you add this up, you get 1.8396 p. I still don't know what p is. Moments going the other way are 0.2 times the mass of r times g, plus 0.655 times the mass of the circle times g. So this is just from what we worked out before. And if I express the mass as rho times the area, and I do the same way again, I get 5.14 times rho. So now I have to worry about what rho is, because I can't just cancel it, because there's no rho that shows up in the other one. So what I am told is that the prism has a weight of 15 newtons. So that means that the mass of the rectangle plus the mass of the circle times rho is equal to 15. And from this I can solve for rho. So I can solve, and I find that rho is equal to 1.167. Now I can equate these two things. And if I do, and I solve for p, I get p is 5.14 times 1.167 divided by 1.8396, which is 3.26 newtons. So that was actually not painless at all. The important thing is it's a lot of geometry and trigonometry and making sure you get the distances correctly. But yeah, it's kind of, I really don't like the first sentence of this sub question. It's really opaque, but there you go. Best thing is to try and piece it together. Right. Last sub question. Find the smallest value of the coefficient of friction between the prism and the ground. Well, this is actually much easier. So firstly, we have to balance horizontally. So this is about slipping versus toppling. So moments are about whether something's about to topple, as in rotate around a point, really, whereas the coefficient of friction is stopping it from slipping on the ground and moving around. So horizontally, the forces must balance. So Fx is going to be P sine of 60 degrees. That's the vertical component of Px. And that's equal to 2.82 newtons. That's the only thing acting in the x direction, because the other two are just weights. In the y direction, we've got the full weight of the prism. I can just talk about the full weight because I don't care where it's acting anymore. Minus P cosine of 60, and that's 13.37. And we know that that's going to be equal to the reaction force. We also know that mu r is equal to the force of friction. So if I want the force of friction, the minimum it needs to be is to combat this, this f of x. So mu times the reaction force, which is 13.37, has to be, at minimum, 2.82. So mu must be 0.211. Okay, rotational motion. This is actually a fairly gentle question, I think, to wrap up with. So we've got a ball moving in this cone. So I imagine the cone's being spun, or for some reason it's being given some velocity, and it's just spinning round and round this circle in the cone. And the big equations that you need are that the force, centripetal force, is which is ma, is mv squared over r, which can also be written as mr omega squared, because v is equal to r omega. And I think the next question we'll need to use the tension in a string equation, but who cares? So, right, first thing is just this thing moving around, and they want to show that want you to show the magnitude of the force exerted by the cone on B. Well, that's just a reaction force, right? That has to act exactly like so. And so it's going to have a vertical component and a horizontal component. And what else is acting on B? Well, the weight is acting vertically, and the centripetal force is acting horizontally. So these must all balance if the thing is not to be moving from where it is. I mean, it's moving rotationally, but it's not going into the cone or rising up into the air, and it's not going into the center. So we know that let's say F that we've been given, we should work out the angle first. So if that's 60 degrees, that means that must be 30 degrees. And if this thing is acting straight out, that's 90 degrees. Therefore, this is 60 degrees as well. So we have F, our vertical component is going to be F sine of 60, and that's going to be equal to mg. And we know m, we know g, we know sine of 60, so we've got our F here as required. And now they want us to calculate the angular speeds. The angular speed, by that they mean omega. Speed means v, but angular speed means omega, so that's in like radians per second. So we have the force, the centripetal force is mr omega squared, as we said before, and this must be equal to the horizontal. Sorry, the centripetal force is like so. Oops. And I'm doing the wrong direction. That must be balancing the reaction force from the cone. So the reaction force from the cone is F cosine of 60 degrees. So we know m, we know r, we know f, we know cosine of 60, and this can give us our omega, which is 3.8 radians per second. Don't get this confused with frequency. So this is angular speed, also called angular frequency, different to frequency f, but they only differ by 2 pi. But that's, I hope you, if you need to know that, I hope you know that. Otherwise, don't worry about it. Now, in the next question, what they've done is they've attached a string. So let's redraw that cone. And so here is where the thing is at. And now there's a string, and it's attached to the ceiling somewhere. And this distance here is 0.3. So now there's going to be a tension in the string, right? Imagine that goes through the center. There's going to be this T acting like so. So this triangle here, it's both a force triangle and a physical distance triangle. So the ratios between sides are going to be the same. So these are going to be two similar triangles. And the one is going to have a height of 0.3 and a base of r, which is 0.4. And if you put that into calculator, you find that means that this is 0.5. And we compare that to the this scenario, and let's call this angle theta, then we get that the sine of theta is 0.3 over 0.5. So therefore, this theta is the same. And we get that this is equal to t cosine theta, and this is equal to t sine theta. And therefore, I'm just going to redraw this. This triangle of forces, so the forces resolved, are equal to t times 0.3 over 0.5 and t times 0.4 over 0.5. So that's how you make the analogy between the physical, that angle is going to be the same, right? That's just what the angle is. And so if we can find out what the angle is using the spatial triangle, we can find out resolve the forces in the same way, because the angle is the same. It's just an angle. So what we have is we're going to be balancing forces again. So we've got this elastic string. So we know that T must be equal to lambda x on L, as I warned you. And we're now going to balance forces in the vertical direction. So again, we have mg. We have the reaction force acting like so. F sine of 60. But it's a new f prime. Now this is important because they say the ball is moving on the surface of the cone in the same horizontal circle as before. So that means that even though we've added this extra force, which in the vertical direction is acting upwards, the thing is not coming off the ground. So F must have gone down to compensate so that the thing stays in the same place. So we're going to say that mg, in our new scenario, mg is equal to f prime sine of 60, where f prime is our new f, plus the tension times 0.3 on 0.5, which is our vertical component of our tension. And so f prime is, mg minus lambda x over L times blah, 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 blah. You get the point. So now we've got our new f. And now we can do the horizontal direction. So just quickly notice that there is a light elastic string of natural length 0.45, and it's now been stretched to 0.5. That's the hypotenuse. That's where the string is stretched. So delta x, the amount it's been stretched is 0.05, and that gives us that x there. Now, in the horizontal direction, we have the centripetal force pushing that way, mv squared over r, and that's balanced by the forces that point that way, which is f prime cosine of 60 degrees plus t times 0.4 over 0.5. So there you have it. You can solve this for v. So we know m, we know r, we know f prime, we just got it. We know cosine 60 degrees. We know t because it's just given by this formula, and we know those numbers. And that will give you the full speed of b. Okay, I hope that was really helpful. Please let me know if you have any questions or you would like to discuss anything, and I will see you next time. Bye.